My dear friends, welcome to Rajashekar classes on applied data science with Python. This is lecture number 421. In this lecture, we will try to understand regularization and shrinkage. So the formulation for the final model in gradient boosting, basically Fm of x equal to h naught plus sigma I m equal to 1 to capital M gamma m into hm of x. This is what we saw in previous lecture. What is capital M? Capital M is the number of base models. We also used k for this earlier. Earlier we said that k is the number of base models, but I am using capital M here because we saw on Wikipedia that they use capital M, basically its number of base model. Whatever variable we use, as number of base model increase, what happens? Your chances of overfitting increase, also variance increase. As capital M increases, or number of base models, as number of base model increase, your bias certainly decrease. As we saw, variance also could increase. This is how you do bias variance trade-off in gradient boosting decision tree. But there is one more nice idea, is called shrinkage, that is often used in the case of gradient boosted decision trees. In general, gradient boosting. In gradient boosting, there is a concept called shrinkage, which is very ingenious. Let's go to Wikipedia page and quickly understand shrinkage. How do you find optimal number of base models? We find it using cross validation or standard tool, because number of base models is hyperparameter, because as it changes, as number of base model changes, my bias variance trade-off will change. It's a hyperparameter that I can evaluate using cross validation. In addition to it, there is a nice hack called shrinkage. What is this? Very nice idea in gradient boosting. Shrinkage works like this. What is our typical model? Earlier we saw, what is model? Earlier we saw model at stage M is basically model at stage M. What is your model at stage M? This is model at stage M is basically model at m minus 1, isn't it? That you have at the end of stage m minus 1 plus gamma m into hm of x. Isn't it? What is this f m minus 1 of x? What does it mean? Your f m minus 1 of x is model we had at the end of stage m minus 1. What is your hm of x? This is the model. This is the model we trained at stage m. Model trained at stage m. What is your gamma m? Gamma m means what? It is, this is coefficient that we got, isn't it? Gamma m is the coefficient that we got. And what is your fm? Fm is, what is this fm? Fm means it's, I can say yes, fm, this is fm of x, isn't it? What is my fm of x? This is the final model that we have at the end of m stages. Now shrinkage is a very nice idea. What it does is this formulation. What is this formulation? Just see, to this, it's simply to, what is shrinkage? Just see, in the case of shrinkage, what's happening? You are multiplying. Just see, same model you are taking, simply you are multiplying. To multiply what to this formulation, it's simply multiply with mu, isn't it? Just see here, gamma m hm x. Just see, gamma m HMX, isn't it? Which one you are multiplying? You are multiplying with the nu, isn't it? Yes. What is this nu? What is the, where will it lies? 0 less than, nu less than or equal to 1, isn't it? Let me, nu is called learning rate. What is this nu? Nu is called learning rate. And remember, nu lies between 0 and 1. Typically, that is 0 less than, nu less than or equal to 1. Typically, nu roughly nu can take 0.1. Of course, nu is also hyperparameter here. Now, let's see what happens if nu is small. If nu is small, what happens? Let's start this. Nu is also hyperparameter. Let's not forget this. This is called shrinkage value. What is this nu? Nu is known as, what is this? This is shrinkage value. This value is known as shrinkage. This is called shrinkage value. Nu is also hyperparameter. How will you determine hyperparameter? We determine hyperparameter using cross-validation dataset. But intuitively, if you think about it, if nu is very small, let me say nu is very small means, let me say nu equal to 0.0001. Very small. The only requirement is, what is your requirement? Your 0 less than, nu less than or equal to 1. Yes, anyway, this 0.0001 is in between 0 less than, nu less than or equal to 1. For example, if what is the maximum value of nu? Nu equal to 1, then that is if I say nu equal to 1, what happens? If I keep nu equal to 1, this is old model. In the old model, it is 1. Nu is 1, isn't it? Nu equal to 1, then it is old formulation. If it is small, we are saying that we are giving, in addition to whatever weight we found using gradient boosting, we are going to reduce that weight. If you are giving nu equal to 0.0001 means you are going to reduce its weight. This is this model. Just see, that's what it says. You are reducing weight. If I keep 0.0001, I find gamma m. What is this? Gamma m nu, otherwise is gamma m, by solving a small optimization problem. And what I can say? I am saying I will reduce gamma m by constant nu, isn't it? I can reduce gamma m. I can reduce this gamma m by constant nu. Now, if nu is very small, what I am saying literally is that I am going to give less weightage to this model Hm of x. Isn't it? What is this model? If mu is very small, I am giving less weightage to the model Hm of x. Isn't it? So, what happens is, as nu reduces, your chance of overfitting reduce. In other words, your variance also reduces. If nu is large, nu can be at most 1. Maximum value of nu is 1. As nu increases, your chances of overfitting or variance will also increase. You have two parameters at the end of the day. Capital M, what is my capital M? Total number of base models, and nu, which is the shrinkage. Nu means what? It is shrinkage coefficient. Of course, ideal thing would be actually do cross validation with the grid search. Cross validation with grid search or random search on both these variables. You have capital M, which is number of base models, and you have nu, which is shrinkage. We do grid search on both of them and find the best ones. Whichever value of capital M and nu reduce your cross validation error to the minimal. That's ideal way to do it. But both capital M and nu used to control your bias variance trade-off. To control your overfitting, whatever you are overfitting or not, whether you are overfitting or not, because remember, in GBDT, it's very, very common. One of the most common thing I see when I apply gradient boost GB or specifically GBDT, people often overfit. It is very easy to overfit, because if your capital M is very large, it's going to trivial to overfit the model to the training set. It's going to be extremely easy. So very cautious to train a model. Always use your cross validation data, and please do grid search on new and capital M, so that you find the best value of capital M and new, isn't it, without overfitting. Otherwise very going to be very commonplace. I have seen lot of cases where people train GBDT and trivially overfit, and say they would take capital M equal 2000, very large value, they would trivially overfit. So be careful. Always use cross validation to get your hyperparameters. Here you have two hyperparameters, shrinkage new and number of base models. This is how you control urge to overfit. So be careful, don't overfit GBDTs. If you overfit GBDTs, their power is gone. But you are very cautious not to overfit. Just go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.